Hey everyone, welcome to a deep dive where we really get to see the unseen. We're talking about radiomics, where we basically take medical images like X-rays and CT scans, and we extract data from them, stuff that you wouldn't be able to see just by looking at the picture.
Yeah, exactly. It's kind of crazy how much information is actually packed into these images,
Hmm.
way more than we can see with just our eyes. And radiomics really helps us unlock all those secrets.
Okay, so before we get into the specifics, can you give us a quick overview of how radiomics works? What are the steps involved?
Sure. Think of it like a recipe, right? With 6 main ingredients.
Okay, a recipe. I like that.
Yeah. So first, obviously, you need the images.
Right.
Whether it's X-rays or CT scans, MRIs, that's
Yeah.
like our starting point,
Makes
right?
sense.
Then we got to kind of zoom in on the important part of the image, like a tumor or a specific organ.
Right.
We call that segmenting the region of interest,
Oh, okay.
or ROI.
ROI, got it.
Now, from that zoomed in region, we extract features. You can think of these as like numerical descriptions of the image. So things like how bright it is, the textures, the shapes,
Mhm.
all turned into numbers we can actually work with and analyze.
Okay, so we're quantifying those visual elements,
Yeah.
basically.
Exactly. Then there's some, data cleanup.
Uh-huh.
Like we remove noise and we pick out the most important features. This is called pre-processing, and it's almost like tidying up your workspace before you actually get started on the real work.
Okay, I could definitely relate to that.
Yeah.
So what's the next step after we tidy up?
Now comes the really interesting part. This is where we build what we call artificial intelligence models or algorithms that learn from all the data that we've prepped.
Okay.
These models, they're like super smart detectives.
Oh, cool.
They can help predict diagnoses, they can suggest treatments, they can even predict how a patient might respond to therapy.
Wow, so they're doing a lot of heavy lifting. But it must be important to understand how the AI is making those decisions, right?
Mm.
We don't just want to trust it blindly.
You're totally right, and that's why the last step is all about what we call explainability. So being able to actually understand why the AI model is making certain choices, this helps us actually trust its recommendations.
That makes sense. Transparency is key. So where does GLCM fit into all of this? Which step are we talking about?
Great question. GLCM comes in during the feature extraction step. Remember those numerical descriptions we talked about?
Mm-hmm.
We group them into different levels, and the simplest ones are what we call first-order features. And these describe the basic intensity of the pixels, like, on average, how bright or dark is this area?
Gotcha.
Then we have higher-order features, which look for those really complex patterns and structures. But right in the middle, we have what are called second-order features, and that is where GLCM shines.
Second order features, here we go. All right, so tell us more about GLCM. What makes it so special, and what kind of information does it help us uncover?
GLCR is all about texture. It looks at how the intensity of each pixel relates to its neighbors.
Okay.
Imagine looking at a tiled floor. Some tiles might be darker, some lighter, some smooth, some rough. GLCM helps us describe that overall look and feel in a way that computers can actually understand.
Okay, I'm starting to picture it. So it's not just about the individual pixels, it's about how they relate to each other. It's kind of like, I don't know, a social network for pixels.
Uh-huh, yeah. That's a great way to think about it. That's what makes GLCM so powerful. It picks up on subtle changes in texture that can be super important for making a diagnosis. Sometimes those tiny variations can be the first clue that something's not right. Plus, GLCM has been around since the 1970s, so it's a well-tested technique with a proven track record.
Wow, a classic method that's still relevant today. That's pretty awesome. But okay, how does GLCM actually work? What are the nuts and bolts?
Well, to understand GLCM, you need to understand its 3 main settings. These are distance, angle, and number of gray levels.
Okay.
Imagine that tiled floor again. Distance is like saying, okay, I'm going to look at tiles that are 2 steps apart. Angle is like saying, I'm going to analyze tiles along this diagonal line.
Uh-huh.
And the number of gray levels is like saying, I'm going to group all the tile shades into, say, 5 distinct categories.
Right. So basically, we're setting the rules for how we're going to analyze the texture. Makes sense. What do we do with those rules then?
Those rules help us build what we call the GLCM matrix, which is basically like a table that counts how often we see different combinations of pixel intensities at those specific distances and angles that we set, right? So it's like we're taking a survey of all the tile combinations on our floor.
Okay, so like a grid almost.
Yeah.
With rows and columns representing the different gray levels and the numbers in the cells, telling us how many times we find those combinations.
Exactly. Let's try to simplify this with an example. Imagine a small image with just 4 gray levels. Let's call them 0, 1, 2, and 3.
Okay.
We set the distance to 1.
Meaning we're looking at neighboring pixels.
Yes, right next to each other. And the angle to 0 degrees, so we're scanning across rows.
Right.
Now we create a 4x4 matrix. 1 row and 1 column for each of our gray levels.
Okay, I'm picturing that. So now, how do we fill in the numbers in that matrix? How do we actually do the counting?
We go through the image and we look at each pair of pixels based on our distance and angle settings. For each pair, we increase the count in the corresponding cell in the matrix.
Okay.
So for example, if we find a pixel with intensity 2 next to a pixel with intensity 1, we'd increase the count in the cell at row 2, column 1.
Got it. So the more often a particular combination appears, the higher the number in the cell. Kind of like a popularity contest for pixel pairs.
Exactly, haha. And one more thing, we often create what's called a symmetric GLCM,
Okay.
which is basically like getting a more complete picture of the texture. We do this by considering pairs in both directions, not just one.
So instead of just going from like left to right, we're also going right to left and combining those results.
Right, exactly.
Got it. But this matrix, this is just the beginning, right? What do we actually do with all those numbers?
Yeah, you're right. The matrix itself isn't the end goal. Think of it more like a treasure map that leads to more valuable insights. From this matrix, we calculate a bunch of features that describe the texture in a lot of detail.
Okay, so the treasure hunt continues. Tell us about these GLCM features. What kind of secrets do they reveal about the image?
Yeah, so these features each kind of capture a different aspect of the texture. They give us like a much deeper understanding of what's going on in the image. So one of these is energy.
Okay.
Energy tells us how uniform the image is. If the energy is high, it means things are pretty consistent, like a smooth surface.
Okay, so like a perfectly smooth wall would have high energy, while a bumpy, textured wall would have lower energy.
Yeah, exactly. Then we have contrast. Contrast basically measures the variation between light and dark areas. High contrast means big differences, like a black line on a white background.
Ah, so like the edges of objects would really bunk up the contrast score.
Exactly. Another feature is homogeneity. Homogeneity tells us how similar the pixel values are within a certain neighborhood. High homogeneity basically means things are grouped together in similar shades, like a patch of grass or like a healthy area of tissue in a scan.
So if we were looking at a lung scan, high homogeneity in a certain region might be a good sign, while low homogeneity could mean there's something disrupting that smooth texture.
Yeah, that's a great way to put it. You're thinking like a radiologist already. Now let's talk about entropy. Entropy measures how random or complex the texture is. High entropy means things are all over the place, kind of like static on a TV screen.
Got it. So if we're looking for signs of disease, areas with higher entropy might be suspicious, right? Because they're less organized, less predictable.
Yeah, exactly. Now, we have two more features. We have correlation, which looks for linear relationships between pixels. High correlation means you can kind of guess what's coming next because there's a repeating pattern. And finally, we have dissimilarity, which measures the average difference between pixel values. So high dissimilarity means there's a lot of variation, like a colorful mosaic.
Wow. Okay, that's a lot of features. It's amazing how they all kind of work together to give us this detailed picture of the texture. But I'm still a bit fuzzy on how we actually calculate them from that GLCM matrix. Can we maybe walk through an example?
Sure. Let's go back to our simple matrix with those 4 gray levels, remember?
Mm-hmm.
The one with the counts of how often different pixel pairs showed up. Each feature has its own way of using those counts to get a single number that represents that feature for the whole image.
Okay.
Like to calculate energy, we square each count in the matrix, add them all up, and then divide by the total number of pixel pairs that we counted.
Okay, so the more often a specific pair shows up, the more it's going to boost that energy score. Makes sense. What about contrast? How do we get that?
For contrast, we look at how different the pixel values are in each pair. So we'd take the difference between each pair of gray levels, square that difference, multiply it by the corresponding count from the matrix, and then just add up all those values.
So the bigger the difference between the two pixels, the more it contributes to the overall contrast score. That's really interesting. It's like each feature has its own way of looking at the relationships in the matrix.
Exactly. And don't forget about normalization.
Right.
When we're dealing with real medical images, the pixel values can be all over the place, right? So normalization is basically adjusting everything to a common scale. It's like making sure we're comparing apples to apples.
Normalization is key.
Uh-huh.
So we've talked about GLCM for 2D images, but can we use it for 3D images too? Like, those really detailed CT scans?
Absolutely. We can definitely use it for 3D volumes as well. There are a few extra steps involved, of course. Like We have to do something called padding the volume. This ensures that all the shapes line up nicely for our calculations, but the core concepts are basically the same.
Padding. Is that like adding extra space around the edges of the 3D image so that everything fits neatly into our calculation?
Yep. That's a good way to put it. It's like making sure all the pieces of a 3D puzzle fit together perfectly. And for those of you who are interested in maybe exploring this a little further, maybe writing your own GLCM code, there are a ton of resources out there. Things like scripts on GitHub that actually show you how to calculate everything. It's a great way to get some hands-on experience.
That's awesome. It's so cool that students can dive in and experiment. We've covered a lot today. We started with this big picture view of radiomics, and then we went all the way down to the tiny details of GLCM. What would you say are the key takeaways for our listeners?
I think it's just amazing that we start with something so simple as like pairs of pixels,
Yeah.
those tiny little dots that make up an image. And then using GLCM, we end up with these really powerful features, stuff we can't even see with our own eyes. Yeah, it really shows how powerful computers can be. GLCM gives us all this quantitative data that's like a whole other layer on top of what doctors can see. And remember, this is just one piece of the puzzle. There are so many other features and AI techniques being used out there.
It's exciting to see how all this is like leading to better diagnoses and more personalized treatments and, yeah, better results for patients in the end. It's like we're giving doctors this incredible tool to help people.
Absolutely. And here's something to think about. We've been talking about medical imaging, right?
Right.
GLCM and texture analysis can be used for so much more than that.
Oh, really? Like what?
Well, imagine using GLCM to analyze pictures from satellites, to track things like deforestation or pollution. Or what if you used it to look at microscopic images, like in material science, to figure out how strong a new material is? There's so many possibilities.
Wow. Yeah, that's a great point. So many different ways to use it. Well, thanks for joining us on this deep dive into GLCM. Keep learning and keep exploring because the future of science is in your hands.